Hey everyone, welcome back to Chem Story. Today we're diving into the stereochemistry of three dimethylcyclohexane isomers, 1,4, 1,3, and 1,2-dimethylcyclohexane. We're going to figure out whether each one has any chiral centers, whether the whole molecule is chiral, and how the different stereoisomers are related to each other. But before we jump into the details, I really encourage you to try drawing the structures yourself first. Stereochemistry isn't just about knowing definitions, it's about actually using them on real molecules. If you give it a try on your own before we go through the answers, everything we cover will feel a lot clearer, and you'll get a much better feel for how stereochemistry really works. Alright, let's get into it. First, let's take a look at 1,4-dimethylcyclohexane. We've got four possible structures here, labeled A, B, C, and D. Each one shows a different three-dimensional arrangement of the two methyl groups at positions 1 and 4. The key thing we're focusing on is the direction each methyl group is pointing, whether it's coming forward as a wedge or going back as a dash. If both methyls are pointing the same way, so either both wedges or both dashes, that's a cis isomer. But if one's a wedge and the other's a dash, then that gives us a trans isomer. By going through all the possible combinations of these orientations, we end up with four distinct structures. Now, let's break down the stereochemical properties of these structures. None of them have chiral centers. The carbons with the methyl groups, positions 1 and 4, each have two identical carbon attachments, so they're not bonded to four different groups. And without any chiral centers, the molecule as a whole can't be chiral. On top of that, each structure has an internal plane of symmetry. So even if we imagine flipping the molecule or rotating the methyl groups, it still ends up being superimposable on its mirror image. In other words, none of these structures are chiral. At this point, you might be thinking, wait, if they have a plane of symmetry and match their mirror image, doesn't that make them mesocompounds? It's a great question, and the answer is actually no. Here's the key idea. For a molecule to be meso, it has to have chiral centers, plural. A mesocompound is one that has chiral centers, but still ends up being achiral because of internal symmetry. But in this case, 1,4-dimethylcyclohexane doesn't have any chiral centers to begin with. And if there are no chiral centers, the concept of meso just doesn't apply. This is a really important distinction to keep in mind. Just having a plane of symmetry isn't enough to call something meso. It also needs chiral centers. So while these structures are achiral, they are not mesocompounds. Now let's look at how these four structures relate to each other. A and D turn out to be identical, and B and C are identical as well. But when we compare A and B, or A and C, or B and D, or C and D, those are diastereomers. Now you might be wondering, how can they be diastereomers if there aren't any chiral centers? That's a fair question. The answer comes from geometrical isomerism, specifically cis-trans isomers, which fall under the broader category of diastereomers. They're not mirror images, but they have different spatial arrangements, so they're classified as diastereomers. So to sum it up, 1,4-dimethylcyclohexane doesn't have any enantiomers, since there are no mirror image pairs. But it does have diastereomers, thanks to the cis-trans relationships. Even though chirality isn't involved here, stereoisomerism still matters, and that's what makes this example so useful. Now let's move on to 1,3-dimethylcyclohexane. Since we already talked about the key stereochemistry ideas earlier, we won't go over every single step again. Instead, let's focus on what's different here and what it means for the stereochemical outcomes. The big difference with 1,3-dimethylcyclohexane is that, unlike the 1,4 isomer, which didn't have any chiral centers, every stereoisomer of 1,3-dimethylcyclohexane does have chiral centers. And that makes the stereochemistry a lot more interesting, and a bit more complicated too. If we take a closer look at the structures, we'll see that each one has two chiral centers. But that doesn't automatically mean that every structure is chiral. Some of them actually have an internal plane of symmetry, which makes the whole molecule achiral, even though it has chiral centers. That's the case for structures A and D. Because they have a plane of symmetry, they're superimposable on their mirror images, which means they're not chiral. In fact, they're considered mesocompounds, and since A and D are mirror images and identical, we count them as the same molecule. Now let's look at structures B and C. These don't have any internal symmetry, so they're truly chiral. They're a pair of enantiomers, non-superimposable mirror images of each other. As for the other relationships, when you compare A to B, A to C, B to D, or C to D, those are all diastereomers, since they're stereoisomers that are not mirror images. So overall, 1,3-dimethylcyclohexane gives us a much more interesting stereochemical picture. We've got mesocompounds, enantiomers, and diastereomers all in one set of isomers. And that's what makes this isomer more complex than 1,4-dimethylcyclohexane. Finally, let's take a look at 1,2-dimethylcyclohexane. This time, the two methyl groups are sitting right next to each other on adjacent carbons, and that has a big impact on how the different stereoisomers relate to each other. Interestingly, when we compare 1,3-dimethylcyclohexane and 1,2-dimethylcyclohexane, we find that they follow the same stereochemical pattern. Every stereoisomer of 1,2-dimethylcyclohexane has two chiral centers, but again, not all of them are actually chiral. Some of the structures have an internal plane of symmetry which makes them achiral, even though they have chiral centers. Structures A and D fall into that category. They both have chiral centers, but because of symmetry, they're superimposable on their mirror images. So they're considered mesocompounds, and in fact, A and D are identical to each other. Now let's look at B and C. These don't have any internal symmetry, which means they're truly chiral. They're a pair of enantiomers, non-superimposable mirror images. So just like in 1,3-dimethylcyclohexane, B and C form an enantiomeric pair. So what about the other pairings? Any other combination, A with B, A with C, B with D, or C with D, represents a diastereomeric relationship. And through all of this, we can really see how the position of the methyl groups on the cyclohexane ring shapes the overall stereochemistry. 1,4-dimethylcyclohexane is completely achiral, but 1,3 and 1,2-dimethylcyclohexane give us a mix of mesocompounds, enantiomers, and diastereomers. It's a great reminder that stereochemistry isn't just about spotting chiral centers. You also have to consider internal symmetry and how the groups are arranged in three-dimensional space. That's all for today's lesson. If this breakdown helped you out, make sure to like and subscribe, and I'll see you in the next one.